this is the last example on the application. So it's called parallel wires. So this is saying most of the wires at your house, if you put your wire close enough, these two wires, they actually have interaction between each other because of magnetism. That's a very interesting fact. So now I'm gonna show you a demo so that you can know what I'm saying. So see, like on the picture, in the demonstration here, you see two wires. And these two wires, they carry different currents in different directions. And here I have a switch. This is switch will compare the direction of the current. So first, you will see, like right now there's no current. When the switch is turned to this way, you will see the current going upward and downward. And then Vasek will turn the switch to the other way. And then the other way, you will see the current going, which is going upward and upward. So you will see two cases. So case one, this is case two. All right, so let me show you. So you see that, like, so first there's nothing, there's no current, and then it repels, okay? And now when we put the switch to the middle, then the wire come back to itself. And then Vasek will turn the switch to another side, which makes the current going in the direction of as shown in the second case. All right. So now let's study the physics behind that demonstration. So that demonstration is showing you how does two current wire react to each other. If you look at this first current, this first current will create a magnetic field, right? And the first current will create a magnetic field going counterclockwise, which means this current, the magnetic field at this current will be going this way. Follow its tangential line. So the magnetic field generated by the first current at this point is going this way. And since we know the current can react to the magnetic field, so the second current will feel the magnetic field and create a magnetic force. All right. So it will feel a force. If we take a bird view, so imagine that your eyes are here and you're looking downward. If you're looking downward, you will see two currents pointing out of page. And at this end, the magnetic field will be going this way, right? And now you can use your right-hand rule. See, the current is out of page. The magnetic field is upward. Then you will see the force is going to the left at this position. So you can see the force is going to the left. So if the force is going to the left, which means this current, the second current, will feel a force pushing this current to the left. So it seems like this guy and this guy, these two wires are attracted to each other. So when you have two currents going the same direction, they will attract. And they will attract with the force, which you also know already. The force that will feel to this attractive force is basically L, I, and B, where I is a current of a second wire. Feel the magnetic field created by this first wire, and the magnetic field created by the first wire. It's also something we know, right? The magnetic field at this point created by a wire is nothing but mu naught I1 over 2 pi r. So if we put them all together and reorganize it, let's move this L over to the left, and on the right, we will have mu naught I1, I2 over 2 pi r. On the left-hand side, you will have F2 over L. So you can see the force per unit length experienced by this wire will depend on the current of each wire and also the distance between them. So if you have a stronger current, then you will feel a stronger force. If they are very close to each other, you'll also feel a stronger force. So this equation in the yellow box concludes the magnetic force per unit length between two current wire, and the direction in this case would be attractive force. So for the I2, the force would be to the left. For I1, the force would be to the right. You can use the same way to analyze the case where the currents are the opposite, and you will realize that they will share the same force as a magnitude, but the direction will be the other way, it will be repel. So let me show you an example. In this diagram shows two current carrying wire in which direction is the magnetic field due to wire 1 at the position of wire 2. So this wire 1, we want to find the direction of the magnetic field due to wire 1. So the wire 1 has a current going upward. So you can see that this wire 1 will create a magnetic field going this way, right? And therefore, it means the magnetic field, it could be a very large circle. Okay? So the magnetic field created by wire 1 at the position of wire 2 will be into the page. Okay, if you can see that. Yeah. And because it's into the page, you see this is into the page, and this is I2, this is B1. Because this is into the page, so the wire 2 will feel a force. That force would be I cross B. And if you use your right hand rule again, it will be upward, inward, leftward. So you can see the force will be going to the left.